Another fun fact concerning nanotubes. So here's a molecule that consists of 60 carbon atoms, and as you pointed out, it's in the shape of a soccer ball. This soccer ball is very, very small, so small, of course, that we can't see it. It's a fraction of a nanometer across in scale. And so just to imagine how small that is, the buckyball, so here's the molecule consisting of the 60 carbon atoms, is to the size of the soccer ball, which is, of course, much, much bigger. This is something that's macroscopic. As the soccer ball is to what? Anyone have any idea? The sun? Even bigger. The planet Neptune.
That's not bigger than the sun.
Well, it depends on how you define the diameter of the sun, whether you include the corona, etc. But the core of the sun is actually smaller than the planet.
Great guess, though.
I was with him
I'm
on that
impressed.
one. I thought the sun would have been bigger.
Well, if you include the corona.
Okay, I'm glad.
So now,
That's what Nano Jeopardy.
Nano Jeopardy.
So now let's talk about some of the forms of carbon. So the buckyball is probably new to a number of you. These molecules that are made out of carbon atoms. But there are other forms of carbon that you're probably more familiar with. Any idea what this is? This is a model of another form of carbon. Any idea? If you look, each carbon atom has 4 neighbors. And all the links between the carbon atoms are the same. Yeah? You know. Diamond, exactly. So diamond is an example of pure carbon. And because all the links are the same, it turns out that diamonds are very strong. And of course, another property of diamond that you may remember from seeing the rings we saw is it's transparent. Well, in UVM, we have a very large diamond, a hopeless diamond. Maybe you've heard of it. So here you can see it has facets and so on. It's transparent, and it's also very hard. But there's another form of pure carbon that's just slightly different from diamond. So here it is. Any idea what this form of carbon is? This is something that you see practically every day. What do you call it?
Graphite.
Graphite, exactly. So here you have sheets of carbon that are loosely connected. And because they're loosely connected, the mechanical properties of graphite are very different from the mechanical properties of diamond. And so we have a nice demonstration, no problem, to show that. So here we have a pencil which contains graphite. And here's a sheet of glass. Would you like to come up here for a second? If you take the pencil, then you should be able to write nicely on the glass as the graphite, pieces of graphite flake off. So you can see she's writing. I don't know, you can't see it very well, but you can see something, right? So here's a zigzag. And just like the difference between diamond and graphite, there are differences in the properties of these different nanotubes depending upon how you roll them up, whether they're armchair or zigzag or something in between, so-called chiral nanotubes. Now, we had one more demonstration for the mechanical properties. You can get a single sheet of graphite just by using Scotch tape on a piece of graphite. So you can isolate a single sheet of graphene. Would someone like to come down and pull off a few sheets of graphene? Come on down. So if you take a piece of tape and then stick it to the top of it on the curve one. Stick it right to it. Do it all. There you go.
Late 1800s is what they did. So just much like our pencil conducting electricity over there, these 2 carbon rods, which are basically oversized pieces of pencil lead, are going to conduct alternating current from the outlet. And I'm going to get that started by contacting, and what I'm going to do before I get too far ahead, I'm going to switch to our camera. This is a camera that's looking actually through a filter because it's very bright. There's a lot of infrared, so it's filtering out the intensity as well as the infrared light. And it's going to look through a little window, and that's why you can't see anything because the filter's so dark. But once I get the arc struck here, it takes a little bit of doing. You'll see the light over there on the wall. And on the screen, you're seeing one carbon model, the horizontal one. I'm pulling away from the vertical one. And you're seeing a little bit of a plasma there conducting gas in between. So if I pull it off farther, you'll see the gas rise a little bit. And I'll push it back in a little closer. And you can see the tips glowing because it's obviously very hot, conducting a fair bit of current through there. And one of the byproducts of this, which was not known until what year? 1980s, is buckyballs. And the soot, essentially, that's created from this type of arc is actually these types of molecules.
The people who discovered the buckyball won the Nobel Prize in 1986. So it's been there all along in our soot, we just never bothered to look for it.
Yeah. They used to use these in movie theaters, I think, at the time, or lighthouses? Well, yeah, our plants, I think, they used it in lighthouses as well, yeah. Anyway, this is a classroom version used for projection.
So if you like, you're welcome to take home some of our soot.
Plenty of graphite. We can peel graphite all day. Probably for millions of years.
Yeah, layer by layer.
Layer by layer. So a lot of layers then. Anyway, and when I pull it back far enough, it eventually won't sustain the discharge. And go down.
Wow.
That's the end. Yeah. If anybody has any questions, feel free.
Come up and roll chicken wire.
Roll chicken wire. Who would have thought chicken wire was so versatile?
I am. Real scientist. I do. I live right here in Burlington. I do.
Are you a scientist too?
Yes.
Not real. Not quite.
I'm a junior.
I'm a helper.
I'm a helper scientist. He helps us.
I needed one more degree.
He gets the stuff to work.
That means he's a scientist.
Sorry. To you I am, but in our world I'm not. It's hard to say. I don't get paid to say that. That's the big difference. That's how you do it.
Well, I think we can start.
Yeah, I think we can.
Yeah. So welcome. This is the third in a series of 4 presentations on nanoscience and nanotechnology. So what is nanoscience and nanotechnology? It's the study of things at the nanometer scale. So first you have to understand what a nanometer is. And so for that, you might consider what you see every day when you walk around in a city, traffic lights, for example, and the spacing between traffic lights is of the order of many city blocks. And so that's a good chunk of a unit of length that we call a kilometer, right? And then if you look at the light itself is of the order of a meter high. So we've gone down in scale by a factor of 1,000. And if we go down by another factor of 1,000, by looking at, for example, the red light consists of lots of little bulbs called light-emitting diodes, at least in most modern cities. And the bulb is of the order of a millimeter in size, and so that's down by another factor of 1,000 from the meter. And that's still not down to the nanoscale. We would have to go another factor of 1,000, and then another factor of 1,000 to get down to the nanometer. And so if we start at the millimeter and, for example, look at the piece that's actually emitting the light, the active region of the diode, that's of the order of a micrometer. And then if we were to go another factor of 1,000, we might see the individual atoms in the active region of the diode. And so when we start to see atoms and molecules, then we're down at the nanoscale. And so that's the scale where I work, things that are very small, where the laws of quantum mechanics are important. Now, just to give you an idea of how small a nanometer is, in the time that it takes to read this sentence, your fingernail will have grown by 1 nanometer. Or, if you shave, I guess very few of you actually shave, by the time you lift the razor to your face, your whiskers will have grown by a nanometer. So that's how small a nanometer is.
So like when you
So if you were combing your hair, by the time you pick up the comb and start brushing your hair will have grown by a nanometer.
What's the atometer? What's the atometer?
Nanometer.
What's a nanometer?
Nano.
Right now my ear.
A nanometer is a billionth of a meter. Nano means 1 billion.
Too small to see.
Now everyone knows what a soccer ball is, right? A soccer ball? Well, it turns out that there's a molecule that looks like a soccer ball. It's called a buckyball, and it consists of carbon atoms. And so the carbon atoms lie at the vertices of the soccer ball, and there are 60 atoms, 60 carbon atoms in a buckyball. Now, how big is a buckyball? Well, to give you an idea of how big a buckyball is, the size of the buckyball compared to the size of a soccer ball is the same as the size of a soccer ball to what? Anyone know?
Question.
What?
No, I don't remember.
This is really, really small. This is a nanometer across. A soccer ball, of course, is about this size, right? Soccer ball. So a nanometer is to a soccer ball as a soccer ball is to what?
It's bigger.
It's bigger. How much bigger?
A nanometer.
This is a nanometer. This is a nanometer. How big would this be? Yeah.
Earth.
Earth is a good guess. It's close. It's very close. The actual answer is the planet Neptune. So it's even bigger than the Earth.
Neptune is bigger than Earth?
Yes, Neptune is bigger than the Earth. So that gives you an idea of how little a nanometer is.
I thought little Earth is that tiny. So tiny.
Neptune's much bigger than the Earth.
The Earth is small.
Yeah. Not as small as a soccer ball.
Big compared to a soccer.
Okay, well today, I'd like to talk about something that lies in this nano world, something called a liquid crystal. Does anyone know what a liquid crystal is? Yeah.
That thing.
That thing, that's right. We're going to talk about that. Well, everyone's heard of a crystal, right? A crystal, what's a crystal? You take the atoms and you arrange them so that they're periodic, that is, equally spaced. Then you have something called a crystal. So here's an example of a crystal. Once you know the location of one thing, then you know the location of everything else. All you have to do is move by the crystal spacing. Okay? So a crystal is a regular arrangement of things, usually atoms or molecules. Okay? What's a liquid? Well, if you look at water, water's a liquid, right, at room temperature. And so there's no relationship between the location of one molecule of water and the other molecules of water. They're all very much random. So if I know the location of one molecule, it doesn't help me in a liquid, right? And so, in fact, we see the difference between the properties of the crystal and the liquid. A liquid will, of course, fill a container. It will take the shape of the container that's holding it. But a crystal won't, because we have this arrangement that the atoms be spaced regularly. Okay? So crystal and solids are rigid, and liquids are mushy. They will take the shape of the container. Well, what's a liquid crystal? A liquid crystal is a little bit of both. A little bit of both. If you look usually to have a liquid crystal, you need molecules that aren't spherical. So think of these as hot dogs. The molecules are roughly the shape of hot dogs, long and elongated. Then here you have a regular spacing between the layers, so in that extent it's a crystal. But if you look within a layer, if I know the location of one, I don't necessarily know the location of any of the others, and so it's liquid. So it's simultaneously a liquid and a crystal. That's what a liquid crystal is. And so now today we'll talk about some of the properties of liquid crystals. And as I mentioned before people started to come in en masse, the liquid crystals are really everywhere. You see them on computer displays, you see them in cell phones, you see them in digital watch displays, you see them in mood rings, and you'll see some examples of liquid crystals here today.
You're going to do the model.
Yeah.
Put the models first.
So, I mentioned that these liquid crystals consist of molecules that are hot dog-like. And so these are popsicle stick models of different phases of a liquid crystal. So here, the hot dogs, you can see that they're pointing in all possible directions. And so this is kind of a scrambled liquid crystal. We call this the isotropic phase of the liquid crystal. But if we were to cool off this liquid crystal, we'd find that the popsicle sticks start to form these patterns. And so here's a particularly pretty pattern. This is a chiral liquid crystal. And you can see that the order starts to swirl around as I go down. It forms this helix. And in fact, this is oftentimes the phase that's used in displays, like computer screens and cell phones. It's this phase of the liquid crystal that strongly interacts with the light and allows us to see images. And so we'll talk about a little bit why that is. So,
If you want to talk about details.
right. So, because these things are liquid-like, they're very sensitive to different stimuli, like temperature and pressure and electric field. And in fact, in computer displays, it's the sensitivity to electric fields that we use to change the images. And so an example of that is, if I take a balloon, you've all seen this before, on a cold winter's day in Vermont when the humidity is low. Hopefully it'll work today.
I think we need a volunteer for this.
Oh, we do.
Yeah, that'd be nice.
We do.
And
Someone with
I'm gonna pick
hair,
somebody
so
with
it can't be
nice long hair.
Dave.
Yeah, can't. Straight hair.
Okay, so, rub.
And we're gonna generate an electric field
There you go.
by generating some static charge.
Right.
A fairly high voltage on the balloon. At least we hope so. By the way, humidity and static electricity just don't go together
No.
as far as building up high potential. So hopefully the air conditioning will take care of it. So you can face that way. And I'm just going to do this. See what we can do. You can picture her hair as a pile of the hot dog.
That's right, these are the
molecules.
hot dog
Kind of.
molecules, right?
You okay there? Okay, if it gets too hot.
We're gonna cut your hand off.
There we go. Let's see.
So you see how the hair will respond to the electric field.
There.
Well, you can do the same thing with liquid crystals. You can get these hot dog-shaped molecules to align.
There we go. Yeah, you can do this at home, by the way. Guys, if you got a little sister,
Trouble.
Okay. There you go. Okay, well, thank you. I'm sorry about that. You know what? Because you volunteered and your hair is going to probably stay that way for a week, you get the balloon. Now, actually, if you got a brush or a comb, just put a little water on it.
It should come right out.
In about a week. Okay.
Should we show the shutter?
Oh, no, that's right.
The
Shutter's
shutter?
next.
You have
You
to-
had the Polaroids ahead of that.
Oh, Polaroids, right.
I need that
If you have
for my
sunglasses, you know that sunglasses are very useful when there's glare, right? So why is that? Well, because oftentimes these sunglasses have a film called a Polaroid film that preferentially absorbs light that's oscillating in a certain direction. So if you, for example, look out at the lake and take your sunglasses, it will cut the glare. But if you were to rotate your sunglasses by 90 degrees, you'd start to see the glare coming in off the lake. And that's because sunglasses have this Polaroid film to them. And So this particular piece of polarizer lets in light that oscillates in the horizontal direction. And of course, I could rotate it, so now it's letting in light that oscillates in the vertical direction. So if I take two pieces of Polaroid, then I can make Mickey Mouse or Mr. Magoo. But more importantly, yeah, no one knows who Mr. Magoo is.
Among the children, anyway.
So if I take the two pieces of Polaroid film and align their axes, then you should be able to see my face because the light is being transmitted through the Polaroid. But if I rotate one of them, then lo and behold, you can't see me anymore. I'm invisible, right? So here I am. You can see me.
Yes.
Now you can't.
If you hold those up in front of the screen, I think they might be able to see the effect.
Ah, absolutely. That's a great idea.
Everybody kind of see that?
So you can see the light go through, and now when I rotate them relative to one another, now it's dark. Okay? So that's what polarizers do. Well, liquid crystals are the same thing, except I can change the axis just by aligning the various hot dogs.
We'll pass these around. If you can actually do this with one. If you look at the reflection of the fluorescent light off the wall and turn it, you'll see the intensity of the light.
Yeah, because the bright or dark.
The reflected light is actually polarized.
Yeah.
And you can do this outside with your sunglasses off or surfaces.
Off the lake or the room.
You can pass those. Feel free to play with those as long as you want. It's exactly the same effect as having two poles.
Right. And so liquid crystals can be made to polarize just by aligning these hot dog-shaped molecules. So shall we do the shutter? So here's an example of that. Here you'll notice that there's a panel, you can't see through it. That's because all the hot dog-shaped molecules are randomly oriented, and so they're absorbing light of all polarizations. But if we apply a small voltage, then we can align the hot dogs, and you should be able to see through the film.
Now, essentially, we're plugged into the wall outlet, so it's about 110 volts. Your orders of hundreds of volts. When I rubbed her head with the balloon, that was thousands of volts, probably, in that area. So this is a much lower field, actually, and I'm going to hit the switch here.
So you can see
And I'll
it go.
move this around.
So now it's transparent with the electric field applied.
Oh,
So
that is
very-
cool. How's it turning white?
How do you do that?
Because it's made of liquid crystals.
I see
It's liquid crystals that align when you
They
apply
just-
the electric
Those
field.
hot dogs just align all in the same direction.
All in the same direction.
And when it's off, they're kind of just random and you can't see them.
That's right.
Question?
Why do you call them hot?
Oh,
Well, the molecules are hot dog shaped, right? They're
Yeah.
long and skinny.
we tried to pick something that you're familiar with to kind of explain what it's about.
Your favorite food.
That's exactly why we picked it, because we know you guys.
Although I should point out, you shouldn't eat liquid crystals.
Or too many hot dogs. That's what we don't want to go there.
How can you become hot dog?
It's just the shape. It's the shape of the molecule.
You can call it corn.
Corn, okay, corn shaped.
Pick your favorite vegetable, whatever. Green beans, they're kind of green beans.
Asparagus.
That's more nutrition.
Oh, it's plant there.
So what else do we have?
We went to temperature.
So now this is the fun part. Well, it turns out that liquid crystals can be made into thermometers. So here's a film of a liquid crystal, and you'll notice that it's kind of a greenish blue. Right? Now if I put my hand on it, wait a minute, see my hand, and that's because the liquid crystals, when I put my hand on it, they become disordered, and we see a color.
I'm going to pass some of these around. Feel free to take one, and you're welcome to take them home. Just take one right now. A lot of people shut up. Now, later on, those people I talk to wanted more, and I'm just saying, that's one.
Pardon me? Like a mood ring, that's
Yeah.
right. And so these things are used to get maps of temperature fields, you can find hot spots and so on. And that's because the alignment of the liquid crystal depends upon temperature. Now Dave, what's the story with this? This will work.
You're gonna have to send that one back.
Yeah, we'll just send that back.
No, let's see. Oh, Mom, look. We had a bigger one, it would have my butt print.
This work is easy as that one.
Okay, let's process this now.
Anybody with really hot hands?
Me, hey.
Yeah, I bet, yeah, you look like a kid with us. Put your hand on that one first. Oh, look at that blue handprint.
Who's that?
Yeah, okay, now try it on that one.
Whoa, it's me. Oh my God, this
Hold
one
it over longer.
I left it down for a long time.
Yeah.
Okay.
There you go.
Oh, look,
Up.
it's starting.
Yeah. Different color though.
Yep.
Different color.
There's the whole thing black. Yeah, I know.
Okay. So this one, these sheets.
Hey, you have a third one.
Where's my third one?
You lost a sheet.
Maybe it didn't come with it. Maybe I forgot it. That's not the same as the other one. You know, I forgot it.
That's all right.
Well, we used to have 3 different temperature sheets, but now we have 2. But these are made up of different concentrations of these liquid crystals, and they're sensitive at different temperatures. Okay. So the one you put your hand on last is actually a higher temperature liquid crystal. And this is exactly the same one that I have in here, and I kind of propped it up hopefully so we can see this pretty well. And I've got a heating pad here, and I got an envelope which has something in it.
Of course, you can't see what's in it, right?
I'm gonna put it behind there if I can. See what happens. Hopefully that will, oh, there we go. It takes a little bit, but we'll see.
What do you see in the front row?
Whoops, come on, boy. Come on. It's dark. Boy, you know, it works in the lab and it doesn't work when you need it. Huh.
Might be too cold. You know?
Oh, it shouldn't be.
If you do it in a cook building where it's 87 degrees.
Let's try. I got something else on it. We'll put this one back in and we'll try another one. Yeah. Yeah, I got it. Oh, yeah. That's why they call it physics, you know, if there's something else.
Whoa, my
It would work.
Oh,
Oh, that works well.
Let me see if I can hold it up. That's why I had it in that frame.
First shot. So here's the envelope.
Yes, Phil.
You can't see it, but if you put the liquid crystal on top of it,
We'll try it again. Probably cool it off so that won't work. Kind of working. There we go. I moved them. Okay, those are a little better, the other ones.
oh, that's okay.
Those are metal washers. I got one on the machine shop and put it in there. We'll put this one back in and heat it. See, this one's not made out of metal. We'll give that another shot. Here in a minute.
So that's an example of using a liquid crystal to detect hot spots.
And you notice as it cools off.
And the color tells you something about temperature.
That's how they make those thermometers. That, you know, it's just a color change.
No, that's different principle.
That's different, yeah.
Get it back to the black.
Oh, you let it cool off. So if you don't touch it, it'll slowly cool off.
See, for example, this is black.
No, but also, whoa, look at that. Look at that. Mine's cooling off fast.
Mine is really hot.
Okay.
Mine's completely cooled off.
Okay, we're almost there. We're a little bit.
Oh, look. Whoa. Whoa. Look at this. Oh, there we go.
These are plastic refrigerator magnets. That's a you.
Oh, yeah. UVM.
Yeah, that's right, it's supposed to say UVM. Yeah, come on, there it is.
Push on it.
There it is.
What is UVM? University of Vermont.
It's actually Latin for University of the Green Mountains, that's why everybody gets confused. It's University of Vermont, you can just UV. But that would be.
Vermont and Montreal.
Yeah, University, Tata is very bottom, part of my Latin. Yep, that's like, anyway, okay. We're, you're pretty much.
Yeah.
Okay.
Show the LCD.
So one last thing, these liquid crystals are used extensively, as Dr. Carter pointed out, and in these projectors that we see everywhere, okay? Like we're seeing projecting an image right now. So I took an older one that we have at work, and I brought the panels out on top of the projector, okay? And I have those hooked to a little DVD, excuse me. And I got a movie in there, and I'm going to turn on the projector. And this is something you may have to come up to look at. And if you do, these panels laying here are the actual panels, the same type of panels that are right here. So these are the little LCD units, and you can see the wires running through them, okay? And these are just like the ones we just talked about, kind of just like this one, okay? And let's see, that's long enough. And if you come up and look at each one of these little screens, you'll be able to see the movie playing, a little tiny movie, okay? And the way you see the color on the screen is there's a bright light bulb in the projector. It's split up into 3 different pads, and it goes through 3 different color filters, a red filter, a green filter, and a blue filter. And then all those are joined together, overlapped, to make the colors you see on the screen. And the intensity of those colors is varied by the signal changing on each one of these LCDs, okay? And we can kind of simulate the light, because the light's actually down there. I have this kind of a cheap little source here. And so one is going to be green, one's going to be red, and one's going to be blue. And whoops, no, I got to start that back up again. Sometimes this doesn't start up right, but it goes into a funny mode where it won't play. So we'll give that a minute to recover, and it'll start it up again, and it should be okay. Did anybody not get the little LCD? I know some people came in late. How many we got there? 4, okay. I will cut some more off. And if anybody has any questions for the real life scientists, now's a good time to let them fly.
Yeah.
Oh,
Why
there's
did it
Keith.
turn blue sometimes?
Liquid crystals, they align.
There we go.
They randomize
You can take those
based
home
on
with you?
temperature.
What if our hands are cold?
Well, if your hands are really cold, then the liquid crystals will stay aligned. And then if your hand is hot, then it will scramble the liquid
Could
crystals.
you even do this in a hotel when it's hot?
Yes.
If it's not too hot.
Not blue.
All blue. So are we ready? Can they come up and see the LCD?
Yeah, I think hopefully one of the reasons why this projector isn't used is because it goes into this funny mode where it doesn't work, so that's why it got chopped up.
Well, I should take a minute to say that we'll be here again at ECHO on the 14th of August, and we'll talk about ferrofluids and bring some ferrofluids that you can play with. These are magnetic fluids, so you can move them around with magnets. They're a lot of fun. That's another example of nanoscience. That's today. We were here last month and the month before.
Oh, you were?
Yeah, this is the 3rd in a series of 4.
Well, it's misbehaving. People are welcome to come up and look. I'll try to get it going again. You can certainly look at the layout. Unfortunately, the video.
What does nano stand for? Stand for anything?
1 billion.
I'll try to get it to work again. Sorry, guys.
Okay, oh my gosh.
Tell you what, we'll take this off while that's warming up.
1 billion.
If you look inside, you
Yeah.
can see one of the color lights comes in from this side, One comes in this side,
Wow.
and then one comes in from that side. And hits that little black cube right underneath that black part there.
Whatever.
Wow, that's great.
And then all those three different,
Leading it for like 1 billion solar signs.
and then those three different colors, those three different colored images, don't wait too far. Images get overlaid and you get that picture.
Yeah.
Is that really fun?
Yeah, these are the same